Hello, everyone. Welcome to all of you to our second astronomy lecture of the season here at the beautiful Huntington Library. We're always pleased to be back here. My name is Jeff Crane. I'm the Associate Director for Technological Affairs at Carnegie Observatories, which gives me a great privilege working with a bunch of really talented engineers and astronomers that spend their time focused on the development of instruments to use with telescopes. And in particular, I'm really privileged to work with tonight's speaker, Dr. Rosalie McGurk, who's going to talk about one such instrument she's been working on now for some time. Those of you who've attended these lectures in the past will know our director, John Mulcahy, who normally is standing here saying hello and giving introductions. John couldn't be here tonight. He was called to our institutional headquarters in Washington, D.C., but he sent his regrets, and I know he's going to be upset that he had to miss Rosalie's lecture. He'll be back for the third lecture, which is on April 15th, and will be about studying ancient stardust found in meteorites. So speaking of that, I should remind you that you can register for that lecture starting tomorrow morning at 10 a.m., and the tickets tend to disappear in a day or so, set a reminder for yourself if you're interested in that. We're very pleased that these lectures always draw such an enthusiastic crowd, and we're really happy to be part of a local community that values scientific research as much as we do. So thank you for coming. If you want to keep up with our latest discoveries, we have a Carnegie Astronomy newsletter, and there's an address on the back of your program. You can go online and sign up for that if you like, and there'll also be someone after the lecture is complete doing sign-ups in the lobby if you're interested. Erica mentioned earlier, but if you haven't already, please silence your phones. And I'd like to take a moment to do a few recognitions. First off, thank you, as always, to the Huntington, their staff, volunteers. We really love coming here. It's a beautiful space, perfect for a lecture series like this. We'd also like to thank Carnegie staff and volunteers who've helped to make this event happen. And in particular, we want to thank the Norris Foundation for their support, which makes this series possible. So, another reason we're all here, tonight's speaker, Dr. Rosalie McGurk, is a Carnegie postdoctoral fellow in instrumentation. One of the many things that makes Carnegie Observatories a great place to work is that it's one of the few campuses that is still fully invested in an active instrumentation development effort. So we build large telescopes that act as light buckets. They collect light from celestial objects and they bring them to a focus, but we have to build highly customized scientific instruments to collect that light and to help us analyze it. Most often this is done with local group of scientists and engineers, machinists, industrial partners, vendors who all come together to make these instruments happen. It's a very interdisciplinary, multidisciplinary effort. It's a peculiar little subfield in astronomy developing these instruments. You can't just order them online, buy them at a store. They're always customized for our telescopes. So it's really great that to have an active program and to be bringing young people in who are continuing the tradition, learning how to do this stuff. It does require an understanding of optics, mechanics. You have to learn things about electronics, software, and then you have to understand, importantly, the scientific motivations that drive the details of instrument design. So Rosalie is fully engaged in all those efforts, and she's going to talk about that tonight. We were very fortunate that she chose to come and work with us at Carnegie in 2017. She's been working with one of our colleagues, Steve Scheckman, who gave a presentation here a number of years ago about telescopes, and they're designing and building specialized spectroscopic and imaging instruments for the Magellan telescopes at our Las Campanas Observatory in Chile. So Rosalie came to Carnegie from the Max Planck Institute for Astronomy in Germany, where she was a postdoctoral researcher for 2 years, and she worked on, among other things, instrumentation for the Large Binocular Telescope in Arizona. Before that, she received her PhD in astronomy and astrophysics from UC Santa Cruz, where she studied active galactic nuclei and was involved with building an instrument for the Shane 3-meter telescope at Lick Observatory in Northern California. Before that, she was an undergraduate at the University of Washington, where she received bachelor's degrees in astronomy and physics. Rosalie's a very creative thinker, which is an important characteristic for a career in instrumentation. She's also a very eager participant and a valued member of our local our local staff at Carnegie Observatories. She's involved with our postdoc association and many outreach opportunities like this. I know you're going to really enjoy hearing from her this evening and learning about how instrumentation really does underpin discovery in astronomy. So, without further ado, please join me in giving a warm welcome to Dr. Rosalie McGurk.
Thanks, Jeff. Hey, thank you all so much for joining me. Ooh, that was loud initially. So we're going to talk about a new tool to map entire galaxies. As we all mentioned, it's important to have these tools. So then, as you all remember from class last time, we're going to be talking about damped waves, and no, luckily we're not going to, thank God. So we're actually going to talk about an introduction to spectroscopy. We'll talk about long-slit spectroscopy and integral field spectroscopy, all about my instrument, and then future science that we'll do with instruments like mine. And so, astronomy is really the study of light, although recently we did get one other form of way we can see objects, but mostly, astronomers really rely on light to actually study the universe, because unlike those easy sciences who actually can touch the objects they're studying, we don't get to do anything like that. All we can do is collect the light. And so when we're talking about collecting it, the light, this is the silhouette of the Hubble Space Telescope, but if you turn it on the side so that you're actually just looking at how the light travels, it comes in the barrel, it strikes the primary mirror, bounces to the secondary mirror. And by the way, astronomers are not creative about naming things. Primary, secondary, really? But then it's focused into the instrument. And then the instrument proceeds to do basically all the magic. So the telescope is critical, but the instrument, as far as I'm concerned, is where everything happens from there. And so, white light is made up of all colors of the visible spectrum. And thanks to Pink Floyd, everybody knows this picture. But to be clear, you send white light through the prism, and it separates or disperses into all colors. And nature is really already an expert at dispersing light into all colors, as rainbows show us all the time. Although maybe not here because of the lack of rain. So the way we'll be thinking about it in astronomy is you have some sort of white light source, or just a light source, and it sends light through a slit to block out any background stuff, through a prism to actually disperse it out, and then spreads it out into a continuous spectrum. And so if you were lucky enough to survive the inside of the sun, and you could disperse the light, you would actually see that continuous rainbow spectrum. It'd be amazing, and then you would burn up. Whereas if you can heat up a gas hot enough and disperse its light out, you can actually get bright lines that really characterize the gas. So lines like that, for example. And the way we see that on Earth is often through neon tubes. So by heating a gas, or in our case, with neon tubes, by running a lot of electricity through it, you can get it to really glow a vibrant color. And then if you actually disperse it out, you can get, so through a prism, you can actually get all the component colors. And so what that really means is, if you've got all this really hot gas in an excited stage, basically you've got all the electrons in really high levels in the atom. A lot like this child who's been fed a lot of candy and then told they can go to the playground. And so then to get the light to actually decrease its level, go back to the lower stage, it actually emits a photon when it drops to the lower stage. So in order to transition from higher to lower, you can get that photon out. And so that's actually what makes those characteristic lines for that hot gas to low gas. And it's really a lot like a child who's finally come back from the playground and has finally gone to sleep, thank God. So then the third way that astronomers think about gas is you can have a white light source with cooler gas in front of it, say the same gas that was hot before, and once you disperse it out, you see the whole rainbow, from that white light source, but there are actually lines missing out of it, those characteristic lines that were actually bright when the gas was hot. And so that means that our gas was cool. It was in a lower energy state. So it started low, a lot, again, like a sleeping child. And then it got a photon, basically like receiving a lot of candy. And it jumps straight up to the higher energy state, like this child. And so really, to actually see that in astronomy, so we're talking about being in the sun to see just the whole solid continuous rainbow. So that works really well, except that the sun has cool outer layers, and they actually contain all these different elements that absorb certain wavelengths of light, giving us that absorption spectrum that I was just mentioning. And so really, when you blow it up to its proper, beautiful level, this is what it looks like. It's really fantastic. And so really, the main statement for astronomers is you can have different types of atoms, say carbon with its 6 protons and 6 neutrons, or sodium with its 11 protons and however many neutrons. And so since each element has a really unique atomic structure, when you disperse them, each element has a really unique set of colors because of all those different unique electron shells that are all around them. So really, each of these sets of colors are the unique fingerprint, or as people have been reminding me, it's actually a unique barcode. So it's a barcode to identify exactly what element you're talking about, or in this case, exactly what Honeycrisp apple you're talking about, or exactly what navel orange you're talking about. So really, they're unique barcodes or fingerprints. And so every chemistry nightmare, or as we all know, just chemistry in general, sees the elements and puts them, organizes them into a periodic table. Astronomers agree that that's a really good way to organize things, but we really look at it a little differently. Because it's not the atomic number that, well, it is that gives us the unique fingerprints, but this is really how we see them. They each have unique sets of colors and different strengths of those colors. So that means when we just see a beautiful image like this, it is the absorption spectrum of the sun, but it actually tells us exactly what's there in the sun. Whether it's this really strong line being hydrogen, these 2 origin lines being sodium, 3 green lines really signifying magnesium, or even more blue and slightly green lines being hydrogen. So it really fingerprints exactly what those elements are and tells us what's in the sun's atmosphere. And so this is a gorgeous rainbow plot. We don't often look at these gorgeous rainbow plots, unfortunately. My life would be more fun if we did. We often actually look at it just as a graph or a plot, meaning that we put the wavelength or the color on the x-axis with bluer wavelengths over to the left and redder wavelengths to the right, and then brightness on the y-axis. And so, still using this plot, you can clearly see all the different, these dips, these absorption lines that show all these different elements and their presence, but it's maybe a little more compact and maybe a little more precise in how we look at things. So just to remind you, we just covered that emission and absorption lines are unique patterns that identify the elements that are present in gas or stars. So we were talking about our sun. What do the spectra of other stars actually look like? So to get the spectrum of a star, we're not just talking about the brightest thing out. So we do have solar telescopes that help us study the sun, but of course, all the telescopes we'll be talking about for the rest of the time will be telescopes you use at night. So we will use that telescope to focus the light onto our instrument. I picked Vega. It's the 5th brightest star in the sky, and it is going to be up in a couple months. So we focus the light into our instrument, and then right at the entrance to the instrument, we actually need to block the background objects that were in here. See all those other extra stars? They're not what we want to study. We've got to get rid of them. Or just mask them out. Don't get rid of them. And so we use basically a mask that comes in on either side, and we really see a long slit. It's basically, we really want just the light passing through the center of the mask, or the long slit. And then we disperse the light. So when we disperse the light from Vega, what do we see? So Vega in particular has really strong hydrogen absorption lines. So there's actually, the whole family of them that is the unique fingerprint of hydrogen in its atmosphere. So putting a long slit across our object and dispersing that light gives us long slit spectroscopy. So far, we've only dispersed stars, and stars are excellent, but what about other astronomical objects? I mean, there's so many other things out there. So if we try to think about long-slit spectroscopy of Saturn, again, we're really going to have to mask it out. We don't want to look at all of Saturn, we just want to look at part of it. But whenever astronomers start talking about long-slit spectroscopy, they really do actually want to look at the rest of the pretty picture of Saturn. So they don't actually show a mask like this, they show a mask like this. So the green bar is where we're actually taking the light in. So then you can see the background around it. So then when we actually disperse it, so here's a much smaller picture of the slit. So when we disperse it out, we're dispersing with the color or wavelength along the x-axis, and then along the slit, along the y-axis. So that's really fantastic. We're still retaining spatial information. It didn't matter for the stars, but it definitely matters for these more extended objects. And so when we do that, we can actually see that if you go along the slit, you've got light from the ring, we've got a dark spot where there's no ring, the disk of the planet is this big spot, another gap, and then the ring again. So that's excellent. We can actually separate what the ring looks like from the disk and study it. And so here's the whole spectrum of what we actually see, and you may notice there are definitely lines that go across the whole thing, but there's also this dark part. So as much as the rainbows are beautiful, if you actually use a detector to study this, the color or wavelength information is already written into it by being so long and wide. I mean, so we already know the wavelength based on how it's dispersed. So as much as rainbows would be great, it doesn't have to happen all the time. So then when we take this white-like picture and we actually sum up all the light in the blue bin and just plot it via wavelength versus the brightness, so the blue box is the ring and the red line, or the red box, is Saturn's disk. So if we stare at it for a moment, because gosh, there's so many things going on, you can see that both of these objects actually have these absorption lines, and those elements might sound familiar because they actually are in the solar spectrum. So the way we see Saturn isn't by it glowing on its own. It's actually reflecting the sun's light back at us. So the sun's light basically has had a double trip from the sun to Saturn and then back to Earth. So that's pretty excellent. But you'll notice there are some big dips in the red line. And so that means that's actually due to methane in Saturn's atmosphere. So the light gets all the way to Saturn, it goes partly into Saturn's atmosphere, it's reflected partway in, but there's been space where this cool gas could do some absorption, and then it is reflected, the absorbed light is reflected back out. And that gives us these fantastic dips and features. That's pretty awesome. Cool way to study Saturn. So then what about galaxies, my favorite objects? So this is Galaxy 2936 from Uppsala General Catalog. Whatever. It's a gorgeous galaxy. It's up in the winter here in the northern hemisphere. And it's pretty big. So this little bar means that maybe that part of it is 2,000 light years across. So if we actually want to study it, we clearly need to put a long slit across it. That's the only way you would do it. And so when you sort of rotate the picture just to line it up with the plot, so we've got the wavelength again on the x-axis, and we're super zoomed in. This would be a tiny portion of the spectrum. And then we're looking at the galactic radius, or really along the slit in the y-axis, with the center lining up with the bulge. And so you can see the continuum from the center of the bulge. So that lines up pretty nicely. And we definitely see emission lines from nitrogen, hydrogen, and more nitrogen. Excellent. We're really sure there's nitrogen there. And so it has emission lines, but it's wiggly. The other ones were straight. Shoot. So that actually encodes a whole bunch of information that we are really interested to learn more about. And so I will let...
The Doppler effect is the apparent change in wavelength of a wave, depending on the motion of the source toward or away from an observer. Astronomers observe this effect with wavelengths of light, but we experience it with sound as well.
If you've ever stood there on a street corner and you've heard an ambulance go by, the first thing you hear is a very high-pitched noise, as it's, say, coming from your left and passing by you, And as it passes by you, what you hear are lower frequencies, a very low-pitched sound. So what is happening in that instance is, as the ambulance is coming toward you, the sound waves that are getting transmitted by the horn on the ambulance, the sound waves are compressed. As it goes away from you, those sound fronts, you could say, get stretched out. So it corresponds to a longer wavelength and a lower pitch. So you hear a lower sound. The same principle can be applied to light. If you have something coming towards you, you will see it, the spectrum get shifted, but towards shorter wavelengths, and those shorter wavelengths are mainly blue wavelengths. So it gets shifted, they say, toward the blue. If something, and this happens often in astronomy, if something is going away from you, it's going to get shifted toward longer wavelengths, and that's mostly toward the red.
These shifts are classified by the direction they move within the spectrum. Objects moving away from us exhibit shifts to the longer wavelengths. We call them redshifts. Objects moving toward us exhibit shifts to the shorter wavelengths and are called blue shifts.
Awesome. So there's one version of how you could explain this. This is my favorite version of how.
Blue light has shorter wavelengths than red light. When an object in space moves towards us, its light waves are compressed into higher frequencies or shorter wavelengths, and hence we say that the light is blue shifted. When an object moves away from us, its light waves are stretched into lower frequencies or longer wavelengths, and we say that the light is red shifted.
So that was the best video I found to just actually describe this. And perfect for April 1st. But seriously, so the Doppler effect is the change in wavelength or frequency of a wave for an observer that's moving relative to the source of the wave. Whether you're moving or it's moving, doesn't matter. And so if this is the light bulb is actually our star, if you're moving towards someone, if it's moving towards you, you would see it blue shifted. If it's moving away from you, you would see it red shifted. And so this is a different way to look at it. So when the GIF starts over, you can see when the light starts, it's not moving. So all the waves are perfectly concentric right there. As it starts to move, they all get compressed, and so we would see that blue shifted version, or since it's moving away, they get spread out, so you'd see the red shifted version. So, okay, what does that actually have to do with anything? VinylCat will help us actually explore this. So this cat actually is having fun. I know it doesn't look like it. So this side of the cat, whichever side it is always moving towards us, and this side is always moving away from us. So that means that, the tail is blue shifted or the head is blue shifted, and the tail is red shifted in that case. So in all seriousness though, if you look at the center of the galaxy, you'd see an emission line, and it would just be there at the central wavelength of the galaxy. So when this side of the disk is moving towards us, you'll see it blue shifted, so you actually see the whole line moved on that side of the galaxy. Similarly, since that side of the galaxy, the C side, is moving away from us, it's red shifted. So finally getting back to what we were actually talking about, so this particular galaxy, this is showing us that this top portion, the line is moved to redder wavelengths, so it's red shifted, which means that whole half of the galaxy is moving away from us. Similarly, this side is blue shifted, or bluer wavelengths, so that side is moving towards us. So that whole galaxy is actually rotating, around this way, and these lines actually let us see it. And so that's awesome. So these long slits can reveal lines, their structure, their movement, so long slits really miss the big scale structure that I want to study. So if you put a long slit across these objects, there's so much real estate outside of the slits. No. So it's very hard to get the whole picture, and people have done it in the past by actually just, moving the slit across the galaxy or trying to take multiple exposures. That's get really expensive in terms of telescope time. If you have to spend an hour for each exposure, maybe you can only cover one galaxy, sort of, for You only point your telescope 4 times at it. So let's see if you can figure out what these pictures are with only 4 slits to actually describe them. So you guys are better at this than I expected. It is Starry Night. Good job. So we'll test you again. What about this one? It's even red shifted on one side and blue shifted on the other. No? Wonder Woman! Yes! So you see the problem. If you only look at narrow slits, it's really hard to look at it. Very hard to understand, rather. And so this is the Indian parable. If you have, in this case, 6 blindfolded people trying to study this new creature, the elephant that I've heard of, everybody's going to have a really different opinion of what the word elephant means. Whether it's a really pointy spear, whether it's a hose, is it a tree? It could be a rope or a wall or a really floppy fin. But looking at only one part of it makes it really hard to understand what's going on in the whole creature, the whole galaxy, the whole elephant, whichever. So getting the big picture for these types of objects is really important. And so I know definitely one of the possible options is you could just put the whole galaxy through your dispersion mechanism, through your prism. That's a little bit messy, though, because you just took all your spatial information and you also added wavelength information to it. So maybe in the y direction, you still have a fair amount of spatial information that maybe is distinguishable, but in the x-axis, you both got the the x-axis and the wavelength axis. Shoot! So there's really no difference in doing this between the spatial information and the wavelength information. So you just lost your information. Shoot. That's the mild word. So with long slit spectroscopy, we get that narrow window into the presence of elements, how they're moving, what their structure is, but you're still missing the big picture. And so luckily, I'm building an instrument that will give us that big picture. Yes! So we can jump right into that. So when we start talking about we really want to look at the entire field, and of course then we call it the integral field. So every time you see integral field spectroscopy, you can think of entire field spectroscopy, whatever works best. And so, like the picture with the long slit, we take our galaxy, we run it through a telescope, and we focus it. But instead of just focusing it onto a mask, we actually do something way more fun and complicated. So we focus it onto not just a flat mirror, but it actually slices of mirror. A mirror that has been sliced, and then each slice has been rotated. Like this tries to show, it's pointing this part of the galaxy over to this side, the center of the galaxy maybe over here, and the bottom of the galaxy over there. So it just chopped your galaxy up. So now you have tons of little pictures of slices, long slices of galaxy, running around in your system. So you need a set of lenses to refocus the light into basically a whole new slit. So what this just did is it took, a square rectangular image of a galaxy, chopped it up, and made it into a long slit. Spectrographs, we know how to deal with long slits. We got this. So then we just disperse the light, like any normal spectrograph would have done. So cool, except it's still pieces. Still pieces that have been dispersed. So then we really do need to use software to actually reassemble it, but once we reassemble it, we now have what I'll call a data cube. The previous ones were just, images. Fine. These have the spatial information, but then they have a third axis that is the wavelength information. And as you'll see in some movies later in the talk, you can actually scroll through that wavelength axis. So it's really fantastic. It's a 3D version that we don't normally think about when we think about pictures of galaxies. So that's integral field spectroscopy. And we're going to be working on the center part, but first, we actually do need to talk about what telescope we're designing this instrument for. So let's jump right in. We're working with Las Campanas Observatory, which is down in La Serena, Chile. I was there last weekend, in fact. And so this is a close-up of what you actually see when you're standing there at the dorms wishing you were asleep. Or actually maybe preparing for a better night, because the sun is rising right now. So I had slept, but I'd observed so much to take this picture. I observed all night, and then I was walking back to the dorm, and it's so pretty. What a clear sky. What perfect observing we had. So these two telescopes are the Swope and DuPont telescopes, and then these are the two Magellan telescopes, the Clay and the Bade. And so we are working, my instrument will be for the Bade telescope. And so when we talk about the sizes of telescopes, we're always talking about the diameter of the primary mirror. So our diameter is 21.3 feet. So that's like 4 people, 4 moderately sized people if you lay them end to end. That's very large. So it's an extremely large primary, which means we can collect more light and look even fainter. That's excellent. So this is what, will you work? No, yes. So this is what my night actually looked like. So this is my telescope rolling around, we're observing something, probably this direction. And so you can see the beautiful night sky. It's so dark there when the moon isn't up. And then the moon comes up. This is the moon, guys. Not daylight at all, just the moon. Oh, God. It's like it's day. You can see shadows. It's wonderful, terrible. Yeah. So that's what my night looked like. It was really clear and really beautiful. So that was my telescope. Then let's talk about the spectrograph I'm building the instrument for, because luckily we have lots of long slit or multi-slit spectrographs there at Magellan. Cool. So I don't actually have to build the spectrograph. It's already there waiting for me. That means it's tricky. It means I got around to building the spectrograph. Yeah. No, it's efficient. That's what I mean. So this is the wide field imaging spectrograph called IMAX. And so the telescope is over here, and there's a tertiary mirror, again with the not creative naming, that sends the light into the wide field imaging spectrograph. But right as it enters there is where I can put an add-on to IMAX that will actually give it a whole new capability. So we've done the telescope, we've done the spectrograph. All that's left is the center part. And so we've been talking about integral field spectroscopy. Let's make it a little easier. It's an integral field unit because what it does is it takes the entire field of view and it transforms it for the spectrograph to handle. So I'm building an integral field unit. And just to give it the full name, it's the reformatting optically sensitive IMAX enhancing integral field unit. But really, let's be clear, it's the rosy IFU. And so clearly the only logo we could have is a many-colored rose, clearly. But starting to jump in, so what the telescope has a huge field of view. It actually focuses us an area not quite the size of the whole moon. That's really awesome. But this is gigantic, it's too large. So what we are actually doing, we are grabbing a field that is 30 times smaller than the moon. It's that little cute thing in the middle. But that actually is gigantic in terms of astronomy. That's very large. Instruments like this that have been built in the past have a tiny fraction of that field. It's like actually almost the size of the laser dot, if I could hold it still, in the center of that field. So this is a huge improvement. My gosh, it's so much bigger. And really, let's be clear, that size is also chosen because it is the size of our local galaxies. So that's perfect, because we really want to look at our local galaxies. So if we take that image that's been focused by the telescope, what my instrument does to it immediately is chop it into 4 pieces. Let's not mess around. 4 pieces. And so I'm going to pick one of them to show the next step. So there's my one slice of the image. We have to magnify it, make it 3 times larger, and then that image slicer, we chop it into 21 pieces. Forget 4 pieces. That was too easy. Great. So now we've got 21 pieces, and this is only one of the 4. Excellent. So then we take those 21 pieces. We have to demagnify them because we really need to bring the image back to its original size. The telescope sends the instrument a certain size of beam. We can't change that. So we magnified it to chop it up. Now we need to demagnify it to send it into the instrument. So we've got 21 pieces. We can't just send them into the instrument as is. They really need to be reformatted into a long slit. And so we've got all these optics that actually do that, pairs of fold mirrors that help us. And so we lined them up into a long slit, and it was definitely way too long to fit onto this slide. We could have made paper that would do it, but they probably wouldn't let me attach things to the ceiling. So this is the center one, and then there are 9 above and 9 below. Yikes, so that got messy. But then we sent it into the spectrograph, not our problem anymore. But really, this is what the optics of the design actually looks like. So we take the light from the telescope, we take it down in, it focuses, and this is where we chop it into 4 pieces straight up. And so then focusing on just one piece, we send that beam over to our first lens, which magnifies the beam by 3, like I mentioned. It folds the mirror, the mirror folds the light over to our image slicer, and then that image slicer chops the beam up into 21 pieces. And of course, I said it fans the beam out, it redirects the light. It fans it out in a way that I actually can't show you because it fans it out this way. So it's out of the screen and into the back of the screen. So I'm only going to talk about right now just the one piece, the central piece, because that fits on a slide. The rest of them, we really need hollow projectors anytime now. So then, just looking at that central beam, it's sent out to a second lens, which demagnifies the beam, because the instrument needs the same size of beam that the telescope originally sent it. And then we have 2 fold mirrors that redirect and reposition the light to send it down, to position it into a long slit, again, out of the projector, into our spectrograph. So, okay, that was only a quarter of it. This is what the whole thing is going to look like, and this is only 4 of the beams. So the field is chopped into 4 pieces, and there it is doing it. So this beam is hitting the center of each of those 4 pieces. It sends it through, 4 different lenses. It's folded by 4 different mirrors. It's sent to 4 different image slicers, which then each chop the beam into 21 pieces. Ugh, it just got messy. We now have 84 optical paths after the slicing. And they all fan out in the same way as I was describing, and then we reposition them into 4 long slits. Okay, really, what is she waving her hands about? So we sliced those 4 subfields up, and we reformat them into 4 long slits. So if you're looking down into, this was a moon before. So this is the image we're sending the spectrograph. So we took our tiny image here, in the original image, and we just reformatted it, each quarter of it, into a long slit to send into the spectrograph. And so by doing that, it's perfect. It actually means that when we do disperse them, the spectrograph disperses them, the spectra aren't going to overlap anymore. We can reconstruct all of that spatial information. So that's excellent. The slightly daunting part is, it says it on the upper right corner. The field of view, that's excellent, but in real physical space, it's 2.5 feet. That's a nice huggable size. So my instrument's going to be huggable, but those are 84 beams. The optics are, sort of like thumbnail-sized to pinky nail-sized. Oh, good. Oh, good. That's going to be a lot of optics to position. Excellent. I don't have anything arranged for the next couple years, right? Lots of free time. So thinking about this, we were talking about all the dispersion that's happening. This image slicer is fanning everything out into 21 pieces. So here's what the image slicer actually looks like. There's a really great calculator there for scale. It's really small. It's sort of like 3 inches by 1 inch in actual size. Those slices are tiny. That's why we had to magnify the beam, because the slices would have been even smaller if we hadn't magnified it. Oh my God. Would have been 1 inch by like 1/4 of an inch. That would have been, would have been brutal. And so, there again with a dime, that's what you should be thinking about. And that's the fanning. So each of these slices are positioned with respect to each other. They're fanned out by like maybe between 1 degree and 1.5 degrees. So they're really small changes, but over the whole image slicer, it has a huge effect. So sort of to be complicated, here's one of those chopped quadrants fanned out into 21 configurations, or 21 slices being sent into the instrument. So there's our image slicer doing what it does, and there are all 21 beams. Oh, God. And we've even rearranged it. So if I just cut out the last 2 fold mirrors and like the beam that we're sending into the instrument, we even decided to stagger the slits. We didn't make just one long slit that's straight. We actually asked it to move per slice back and forth. Because as you can imagine, if you're just making a base plate, one big thing, and you cut 4 pieces into it, 4 slices, structural integrity just went down the hole. So if you can stagger them back and forth, you can actually regrain a bunch of it. So now, everything should be pretty stable when you have to like move and rotate it. So, and just to zoom in a little, that's what each of them looks like, staggered back and forth. So as a point of scale, that's, the difference between them is 6 millimeters. It's way less than an inch. It will be great. We'll be good. And so this is what, we finally finished the optical design. It's all complete. So we're moving into the actual mechanical design. That's awesome. So this is, if that light was coming over from that slice, we're looking at 5 slices, just the 5 center ones, and our mechanical engineer has it going through those secondary lenses that demagnify the beam, bouncing off that first fold mirror, hitting the second fold mirror, and you can see there's 2 of them are staggered with respect to each other, and then they're sent down into the instrument. So, and there's, if I click one more time, there's windows in here that also have to be a weird shape to accommodate that staggering. Oh boy. So this is pretty small. It's only going to be like this big. It's good. Looks really big there. Pretty small. Should be good. That was the point. So we're really well on our way to actually getting this done. Our plan is to finish the first quadrant, basically, that first chopped quadrant that I've been talking about. We're going to finish it and be commissioning it, hopefully by the end of this year. Sweet. So I don't have much free time between now and then. But once we prove that everything works, we're going to go into mass production. And we hope to finish the other 3 quadrants, since we'll know what we're doing, by the following year, by the end. So should be good. So to sort of state that, this is what we're doing. This is the schematic idea. We use an image slicer, we reform a long slit, and eventually it will become the Rosie IFU. So I'm building this fantastic new instrument to get spectroscopy over a large area. Okay, you guys have borne with me. What science can we actually do with it? Because I said we need to see wide fields. You held on until now. Let's prove it. So this is the new galactic catalog. We're not creative again with our naming. Object 4650A. And so you can see the Hubble Space Telescope image of it. It's got this really fantastically weird polar disk as well as just being a disk galaxy. And it's huge, huge. But we'd really like to understand, how is it rotating? Is that rotating? What's going on? We'd like to understand how it got this way, because it's not our normal disk galaxy that you see pictures of. So an instrument that was built similar to mine has looked at this galaxy, and maybe we can start the road. Yes, there it goes. So if you actually look, if we narrow in on specifically nitrogen, hydrogen, and sulfur emission, it just went by, and it will come back hopefully. You can see from left to right, yeah, there it goes. From left to right, yeah, you're going again. It's busy rotating in this way, but there's not much visible rotation along that central bulge or disk, or whatever it is. And so I think we just flashed through, those were the sulfur lines, and then it started over, and we'll look at a nitrogen line, a hydrogen line, and a nitrogen line, like we looked at before in the long slit spectroscopy. So everything is rotating, and the hydrogen one that lights up the whole area, not just the disk, it's busy showing us that there's both gas and star formation going on around this galaxy. So it's totally conceivable that a merger could have done something like this, flung all that gas out and caused some more recent star formation. But if you tried to put a long slit across it, you'd have to slice up the galaxy basically to get that whole picture. So what else can we do? So this particular galaxy has been looked at by Hubble and by the Chandra X-ray telescope. And it has a phone number of a name, thank you for that. But really, it's a disk galaxy that's falling into a galaxy cluster. And it's actually, what the X-rays show us is that it's got streams of hot gas coming off it. Wow, it's falling into a cluster, and it's being sort of stripped of its gas. What is that gas doing? How is it rotating? Is it related to what the original galaxy is doing? Super can't know until you look at it. And so that's what this is. This is a hydrogen, well, nitrogen, hydrogen, and nitrogen again, because that's one of our favorite sets of lines. And you can actually see the disk itself, the galaxy itself is rotating. just like that. But even more interestingly, it shows that the gas that has been stripped out of the galaxy is still rotating. So it's already been torn from the galaxy, and it still remembers the original motion it had. That's fantastic. We'd really like to understand more. For example, are there gradients across it? Someone already published a paper about it, so we'll have to find some other objects to look at. That's really cool. Similarly, so that was gas stripped from a galaxy. What about a galaxy that's actually blowing bubbles itself? So again, phone number of a galaxy, the New Galactic Catalog, 1275. It's this fantastic galaxy that you can sort of see here at the center, but something else entirely different is going on. It has these really fantastic filaments going on inside the galaxy. And this is sort of a summed up picture of the movie you're about to see. So as you scan through the galaxy, okay, without emission lines, looks like a normal galaxy, good. But once you get to these lines, the movie slows down so you can watch all of these really intricate fibers, filaments, and it's not actually feeding the galaxy. By analyzing, by looking at simulations, for example, movies, we can understand that this galaxy actually has an active black hole in its middle. And so that active black hole isn't just sitting there and eating, it's also, it's really blowing bubbles. And so that's actually what it's showing us. We're like, oh, this could tell us, oh no, it's really just a toddler going, and so it's really got those it's got basically bubbles inside that it's busy blowing, and this is the gas cooling around those bubbles. Now that it's finally been blown out far enough, gotten far away from the hot black hole to actually cool so that we can see it. That's really cool. Of course, one of the challenges in our lives, I had to look really hard to find some of these movies, because astronomers, when you have to publish one of these, you really can't publish movies very well, especially back in the day. So we got really used to just publishing velocity maps. So instead of watching this whole galaxy rotate, like I do in my dreams every night, when you look at this just normal disk galaxy, we put a velocity, a scale bar on the top. So black means that this part, the central part of the galaxy, isn't particularly rotating with respect to us. And that makes a fair amount of sense. So then this side of the galaxy is moving towards us at 180 kilometers per second, which 1 kilometer per second is 2,000 miles per hour. So that's really fast. Check. I had to look it up, and I was really impressed at how fast. Similarly, the other side of the galaxy is moving at 180 kilometers per second. So now that this type of instrument is starting to become more common on telescopes, astronomy is starting to become full of these fantastically colored plots to try to show all these velocities and try to start picking into what is causing, how are these galaxies rotating? What can we learn about them? That's pretty fantastic, because sometimes, gonna not have a cursor, maybe. So this particular galaxy, I'm sorry if it's a little fuzzy. It turns out pretty well. So their integral field unit is this weird hexagonal size. And so if you can see it, this is the velocity of the stars. And they didn't put a scale bar on here, but plus or minus 60 or 100 kilometers per second, still really fast. What's fantastic is the stars, this side of the disk is moving towards us, and that side is moving away. Okay. In the gas, though, they also had some emission lines from gas. It's moving away from us, and it's moving towards us. That's awkward, because we think stars form from gas. And so if it formed from that gas, the stars should be going the other direction to match the gas. Okay, so we have more to learn, right? We're always finding these counter-rotating objects, and that starts to tell us that the gas has come in to the galaxy from a different source. Or it's undergone a merger to turn the gas, so it's eaten gas going a different direction, and the stars were formed quite a while ago. So really, we have a lot to understand about these galaxies. And this data is just starting to come in. We still have so much more to learn. So my instrument is going to be in really good company to start studying these galaxies. So in summary, we learned that spectroscopy of emission and absorption lines shows the presence of certain elements and their movements via the Doppler shift. Long-slit spectroscopy is fantastic, but it only shows a part of the picture. An integral field spectroscopy can show the entire picture, as this shows. And then our integral field spectrograph is going to open up a whole new avenue of galactic science for the Magellan telescope, just like this one is doing with all of its incredible filamentary structure. So thank you so much for your time. I did it.
Good job.
Yay.
Yes, thank you very much, Rosalie. We have some time. If people have questions, we probably could spend 10 or 15 minutes. There is another room with other people enjoying the presentation, and in order for them to hear any questions you have, we'd request that you use the microphones. There are 2 in here. There's one on this side. It would be best if people in the room could use that, and then we'll have this one available for folks coming from the other room. Yeah, so please, even if you have a booming voice, please use the microphone.
Because we want everyone to be able to hear your question.
Yeah.
Any takers? Oh, I see one over there.
Yeah.
Now, hold on. Or if you could actually get up and start going to the microphone, that would be awesome.
My question is, because your little guy is this big,
Yeah.
and you've got all the curves and stuff, how do you know when you've got the right set of curves? Is your data going to verify that, the precision that you have to make that happen? How do you know you got it right?
That's a good question. Do you mean for the galaxies or for the instrument?
The instrument's going to create this data for you.
Exactly.
Yeah, so how do you know when it's right?
So we take all sorts of calibrations whenever we do this. We actually shine known wavelength sources through it, so we can map it out ahead of time. We also shine basically a white light source through, and when that's dispersed by the instrument, it traces out where all of the spectra are, so we know exactly where they should be, and as I said, we shone through a source that maps out those wavelengths for us. So then we're able to calibrate it, and it's a totally good question, because without a great pipeline, you're really toast. So the trick is going to be, and I didn't touch on it here, we have to build some beautiful software. And there are some software packages out there that do this, but it's all customized for such specific instruments. So we get to customize our own set of software to enable people to actually use this instrument, because otherwise it's really going to look like a gobbledygook of lines, and that would be sad.
Yes, thank you very much, Dr. McGurk. I have a question.
Yeah.
So it is still not clear for me, how do you create this 3-dimensional map?
Okay, how I create the 3-dimensional
Yes.
map? Do you mean how to reconstruct it, or do you mean how we spread it out in space onto the detector?
Both.
Both. It's a totally fair question. It's very messy. Oh, you're going to let me move back? Maybe. Here. So the whole challenge is to really send that image onto the image slicer, slice it up into pieces, however many pieces, and then move it, reconfigure it so it's the long slit that we already really know how to disperse. Because once we've got them all strung out so that it's not overlapping the spatial information from each of the slices, and we disperse them this way, for example, or this way, whatever is easier to see, onto our detector, then with the calibrations I was just mentioning, we can actually use that software and say, okay, we know from our calibrations that this piece corresponds to this top slice of the galaxy. This piece corresponds to this slice of the galaxy, and so on. And so that way, using the software, we can put it back together to get that spatial information and then the wavelength information. Because we need both the optics to chop it up so that when we disperse it, the whole galaxy isn't just on top of each other via wavelength, but then we need the software to actually turn it back into that 3D cube.
So when you mention the software, basically it is you implement some sort of algorithm inside.
Some sort of what?
Some sort of algorithm.
Algorithm.
Yes.
So we certainly, I wish we could have used an algorithm to just define the spectrograph. That would have been to do the optical design. So we definitely use different algorithms to extract out where exactly everything is placed onto the detector and how to rebuild that data cube. You're absolutely right. Definitely algorithms.
You spoke about the image being magnified and then demagnified.
Yep.
Is there loss of quality in that process?
Ooh, that's a great question. So in most cases, no. That's actually what telescopes are all about, just delivering you a perfect image, and then you use optics and you can change the size, you can change the well, your detector determines the resolution in the end. But so one of the questions is, depending on how you do your optical design, as anyone with glasses can tell you, you can have a good prescription or a bad prescription. So if it doesn't match your needs, if you do the optical design wrong, you can make images that are really blurry or images that have very poor quality, basically. They can just, it can look lumpy if you looked at a point source. So the trick, of course, is to use optics to design them well so that they will have the best image quality possible. So when we designed it, you know, we're actually worried about every time you slice that image, you're basically saying we want a resolution of the diameter of each of those slices. And so that put a really clear constraint on, okay, in engineering, you're always asking, what tolerance can I have? Because nothing's going to be perfect. Ha! What a great idea. But you always have to talk about what error is within budget, within spec. And so that is exactly a great question, because if your optical design is good enough, it delivers you small enough optical error that it will fit within that slice and therefore still give you perfect images of what you need. So we chose our slice diameter, or size, whatever you want to call it, to be sort of the average, we call it seeing, the average great image quality that we get at Magellan Telescope. So you can design it for the best image quality there, but then you're over-designed and you've maybe made your parts so expensive that they can't be paid for. Oh, what a problem. Similarly, if you make the slices too large, then you're losing quality. That would be terrible. You're using a telescope at one of the best sites in the world, and you designed for terrible image quality? Oh, that's when they fire you. So that's a great question.
Thank you.
That was fabulous, Rosalie. I just thought I should add two little things, if you don't mind. For people who may not know, the telescopes that Rosalie showed in Chile are Carnegie Observatories telescopes in Chile, for people who are here, for example, for the first time. And the other thing is that the instruments that are made with such exquisite precision that Rosalie was showing are made in our machine shop, right there on Santa Barbara Street. So.
Yeah. And I know one of our mechanical engineers is actually in the audience, and I see him right now, and he's trying to hide. He's right over there. So I work with people like Jeff and like Leon, and we build fantastic instruments. And that's really the point. We build instruments that we use. I'm going to do science on this. So it's really not, I'm building something for someone else really far away, and I don't have to think about it. It's mine. No pressure.
Just a question on the challenges. Considering the size of your image slicer, how much of a challenge was the actual surface properties of the mirrors themselves and also cleanliness?
Yeah, that's a great question. So this is actually a prototype. It's not the final design. And we just made it in our machine shop. So when we actually get to this, we're going to use basically, you know all those slides that you used in biology to look at things? So imagine those slides and then forget the face of it. We don't care. We actually care about the edges of them. And so we take all those slides and we stack them up. I normally use phones to show this, but I don't have my phone with me. So you stack them up like this into sort of a puck, a disc, and then we polish them. We give them the optical quality that's needed. And that is pretty straightforward. We really know how to polish optics. We've been doing it for a really long time. So then they've got holes, you can sort of see them, holes cut into them that dictate that precise fan-out angle. So that should be pretty straightforward. We're a little worried about how the edges, I'll use actually the pointer, how these individual edges will react when they're polished, but we think it should be pretty good, because even if there are tiny imperfections, we still are getting the whole slice beautiful. So should be good. Should be challenging, but good. Yeah.
Can you replay the video of the cow being abducted? please?
Can I what?
Replay the video of the cow.
I am happy to replay
Please.
the cow. It would please me greatly to replay the cow. Because it's just so funny. Come on, go back. Oh, why are you so slow? It says, you have such beautiful images, I can't possibly go fast through them. Come on, cow. It just doesn't want to go back. Come on. Oh, almost there. Almost there. Come on. It's like it's doing it in slow motion just to tease me. There's the cat, almost there. One more. Come on. There, cow.
Blue light has shorter wavelengths than red light. When an object in space moves towards us, its light waves are compressed into higher frequencies or shorter wavelengths.
Watch the color of the
And hence we
spaceship.
say that the light is
It's
blue.
blue.
When an object moves away from us,
And now
its
it's
light waves are stretched
and now it's red.
to lower frequencies or longer wavelengths. And we say
Look
that the
at
light is red shifted.
Okay, I think we have time for one more question, sir.
Yeah.
On a similar vein there, I didn't see a credit for Vinyl Cat. Is it one of yours?
For which one?
Vinyl Cat.
Oh, no. I don't know if I actually managed to put the link on it. No, that's had YouTube, although my cat actually looks really similar. She's a little bit bigger and a little chubbier, but there is a credit. It's just blue on purple.
It's coming toward us.
Thanks for the question.
All right, thank you all again for coming out. And thank you, Rosalie.
Yay.
We will be here for a few more minutes if any of you want to ask questions individually. And don't forget to sign up tomorrow for our next lecture on April 15th.
It's going to be